And just for the record, we skipped the end of chapter 14 and chapter 15, which we're going to hopefully do videotape separately and perhaps on Monday during the review. Chapter 16 is a very discrete and very topic, but it has many, many methods, of which we're going to do none of them in the book. We're going to basically show you my own simplified method that works and is understandable and at least gets you into the topic. And therefore, when the people who take it online, I changed the questions online so that the book's method, well, I'll talk to the people online on Monday perhaps about it. No, maybe I should mention it now. For those of you doing the online stuff between now over the weekend, chapter 16, I used the book's numbers, which they give you under the icon. So you're going to have to take those numbers and copy them into your Excel or by hand. Then you're going to, graph it, and you're going to have to answer some verbal questions about it. And eventually, the book's going to ask you to make the forecast, which is the whole point of the chapter, is to make a specific forecast. And the books, and I basically erased the book's answer, but I couldn't put in my own answer because my own answer, since everybody has different numbers, it's algorithmic, it's randomly generated, I'm going to have to mark this by hand. So you're not going to know if it's right or wrong. There's no feedback. And so it's a little bit of a problem, but until I resolve that, just realize the books, they won't tell you if you're right or wrong when you do the homework or the quiz. I would just say bring it into class on Monday or email it to me and I'll double check it. But all right, anyway, let's continue. In time series, basically we're analyzing, again, one variable like we've been doing for the last few chapters, a y variable. But the y variable happens to have is collected over time. So the main difference between this chapter and the previous two chapters, where we're still dealing with x and y's and relationships, is that the x variable, the horizontal axis, is basically a function of time, which we can call t. And in fact, we collect data very regularly at time point 1 and 2 and 3 and 4 and 5 and 6 and 7 and 8 and 9 and 10, etc. Now, these time points could be centuries. Every 100 years you can collect those geological data. It could be every second if you're collecting some kind of biological data. It could be every quarter if you're collecting economic data, but it's some kind of regular time period. And the y variable can be anything: the price of a stock, the unemployment rate, your blood pressure, the amount of global warming, all kinds of variables could be measured along the y-axis. What do we have here? Precipitation. Okay. Maybe Brian, if you don't mind, maybe just you can aim the camera there for a second. On the screen, I looked through the internet to try to find good examples of time series. Turns out there's millions of them, but I'm not sure if I picked the best possible one. But this one represents the amount of precipitation along the coast of New York State every quarter from 1980 to 2010, about 30. Now, how would you analyze this data? Well, first of all, remember this is 2 years worth of data here. This is 2 years. So and they only have one data point. In other words, if they had this, and I try to find something quarterly, because we're going to be focusing only on the quarterly data, which is the most business related. But if you had to look at this thing here, would you see any trend? Well, it seems to be going pretty much horizontal till now. Then the last 10 years it starts going up. So the amount of rainfall is going up. Is that a blip? I don't know. So let me just be careful, guys. I'm gonna. Here's another slide. This is temperature. Now this is temperature from 1980 to 2010. Last 30 years worth of temperature. Do you see a trend? Is it going up? Well, a lot of people see a trend, and basically it's going up, towards a slight, upward trend if you draw a line through this thing. And that's what people are saying is global warming. Other people say, well, if you look at a graph, not just for the last 30 years, where everybody admits there's been an increase in temperature, year by year. Notice some years it gets cold, and it goes up and it goes down. But when you stand back, that's what the statistics gives you. When you look at the basic trend, it seems to be up. But that's just the last 30 years. What about the last 3,000 years? What about the last, 3 million years? So. Maybe they're always every 300 or 400 years. There's a couple of years where it's starting to go up for a while. Now, is that random? Is it something to do with the sun? So this question about is it global warming or not is really very controversial, obviously, and it's a very not a $1 million question, not a $1 billion question. It's a multi-trillion-dollar question. And there are people who say yes, there is global warming. The people who say there's not global warming, and there's we have to learning today's formula will decide, but not really. Now this is an example of, what is this? What is this now? I don't even know what this is. This is temperature, but here we see, okay, I spent a lot of time getting these examples, and I don't really think I accomplished what I wanted to accomplish. So we're gonna move this aside for a minute. Because the point I'm trying to make, which I guess I didn't make with these slides, is that when you're looking at classic time series, it turns out the data has four major components. First of all, there's something called a trend, meaning if you collect data, you're going to get something like this. Okay, there's going to be a trend in the data, and one of our jobs is to calculate the trend. Now we're going to calculate the trend the same way we calculated the trend in chapter 13 and 14, in particular chapter 13, by the B0 and B1. It's basically a straight line, so let's use the formula for a straight line. But there's also built into the time series a cycle, meaning if you look at the data and you sort of look at, you'll see some cycles in the data. So there's a cycle in the data. There's also, if you look at like a mini cycle within 1 year, very often economic data goes up and down, up and down, up and down within a year, quarter by quarter. Let's say, for example, it's a toy company. So obviously, right before the Christmas season, their sales are very high. And maybe during the summer, the sales go down. This is true for the last 45 years. So there's a certain seasonal effect, which you can sort of see as a superimposition on top of the cycle. So it's like a mini cycle within the cycle. So we have something called the seasonal effect. And finally, there's something which is just totally unpredictable. You'll have, even though this is a mathematical theory of what's going on, there may be a dot over here and a dot over here and a dot over here. There's going to be all these outliers, so not outliers I should say, but all this data which doesn't fully follow the mathematical properties of the first three components of the time series. And we call that the irregular factor, the fact that the thing that can't be predicted is totally irregular. Yes? Can I hear you what?
What's the S stand for?
Season. Now, so our job is basically to take a bunch of data. Look, here's the main point of the chapter. Our job is, let's say you have the first 12 quarters of data, which is year number 1 is 4 quarters, year number 2 is another 4 quarters, year number 3 is another 4 quarters, and now we're up to this. This takes us up to the present. And you're a manager or owner of a business or responsible for making a forecast. You want to make a forecast for the very next quarter, which of course you can see what I'm making a big speech about. It's a very important function of someone who runs a business. So the way we did it till now is we figured out the B0 and B1, and then we said, you plug in, let's say, a 13 in for the B1. B1 times 13 plus B0 gives you the forecast. But we're going to do better now, because until now, we assumed that the amount that the data varied from a straight line, one of the assumptions which I mentioned very briefly, but you should be aware of it, that the amount that the data varies from a straight line is totally random, what's called independent errors. The amount that have deviated above the line here, below the line here, below the line, each one was totally random. I mean, an example of that would be something like this, where you have data, something, it's just totally random around the straight line. But here, that assumption is being violated. That assumption that it's totally random is not true, because if you're down over here, you're probably going to be down for the next 3 or 4 quarters, or the next 3 or 4 years, because it seems to be going into a down cycle. And if you're up over here, so here, the assumption of independent errors, the assumption of independent errors is violated. In other words, there's information to be gained by knowing the amount of deviation from the straight line. Independent errors from chapter 13 and 14 is violated, is not true. In fact, so let's take it from a common sense point of view. If you had to make a forecast for the fourth year, the first quarter of the fourth year, and the straight line told you that this is where the forecast is supposed to be. But we also know that the data has been following this pattern for the last 4 or 5 or 10 years, and we're now and for the last couple of years we've been in a down cycle. Wouldn't you take your forecast and chop off a little bit in order to account for the fact that you're in a down cycle? The answer is yes. And what if it turns out that particular cycle happens to be in the summer month, as a toy company, is during the summer month, and always during the summer months the data is always even lower than the typical time